Well, welcome to my channel. I'm going to try to make an analogy between solar cells and a check valve. I hope to also get a understanding on how to use PowerPoint as a way to deliver information. I wasn't real happy with my video phone recordings that are already on my channel. See what happens. You can use any part of my presentation. You can clean it up, incorporate it into yours whole or in part. I don't care about attribution. What I'm trying to do is find ways to help people understand. And I know this subject's been covered multiple times, but here's my take, and this is my test video, basically. All right, let's go through what's in a plumber's check valve. First, we have a diaphragm disc. In a normally seated configuration, this disc would be between this point and that point and close off water flow. What I'm showing here is an open check valve where the pressure in is great enough to overcome the spring force pushing the diaphragm back that way. The valve seat is going to be considered pretty ideal. All right, this orange thing is the spring and the water pressure in. Water pressure is a force. We have several of these in our house. They could be used as pressure relief valves or backflow preventions. And I'm going to relate water pressure to voltage. I've also drawn a tube size for the entrance tube compared to the exit tube, slightly different sizes, to show that, this size reduction can cause a flow resistance, and I'm going to call that R series when we get to diodes. Next slide. Okay, in this presentation, I'm going to show a check valve fully closed, partially open, and fully open. Now, I didn't put the gap in here for the water to flow around it pictorially, but that's because I'm not a very good artist. All right, in this case, the pressure in is less than the spring force. The valve is closed and no water is flowing. All right, we may have some leakage around this valve seat here. In this case, the pressure in is just equal to the spring force, and it just starts partially opening. Okay, and we get very little water flow out. In this case, the pressure in is significantly high enough that we can get full flow limited by the diameter of the exit tube. Okay, now in my ideal diode curve, we could use the same curve for representing these three conditions of water pressure flow. We have a crack open pressure somewhere in this area. We have a full open pressure in this area. And the curve would look like start to flow, increase flow, and then we get a steady state flow out. All right, now let's compare this to a diode. If we assume the voltage across the diode from here to here is positive, and we assume it's similar to a pressure by analogy, and we assume that it's silicon diode, power diode, it will crack open somewhere around 0.6 of a volt and be fully open somewhere around 0.7 of a volt as far as a equivalent pressure. The diode triangle arrow, this little thing right here, points in the direction of the current flow. Now, for physicists out there, I'm using conventional current flow of positive to negative. I'm not going to get into the Compton diode current flow direction. Well, it just so happens we can use a very similar curve. This is the ideal diode curve where we get crack open or just starting to break down, and we get full open. We can get full current flow when it's fully open. Okay? Now I've drawn a tangent line to this curve to try and indicate where the full open point is in pressure or volts. This is a classic ideal diode curve that every electrical engineer, technician, physicist should recognize. The interesting thing about this diode curve is when we get to solar panels, we're going to flip it upside down so that where this graph crosses this line, we have the open circuit voltage. But I'm going to leave that to a different presentation. All right, last thing we have to understand in diodes is called the reverse breakdown voltage, and I'm going to relate it back to a pressure valve, check valve again. All right, the pressure out is much higher than the pressure in. The valve is closed, and if you put enough pressure on this, eventually you're going to break this diaphragm, and the water flow will go backwards. Well, this is also true of diodes, silicon diodes. The reverse voltage is an example of the Zener effect, but engineers want to emphasize the breakdown in the power applications. Okay, if the voltage here gets large enough, we can break down the diode, and it is truly broken. And we can have reverse current flow. All right, the Zener effect, engineers like to reserve that for intentional reverse breakdown, as in Zener diodes. The typical reverse breakdown voltage is 13 volts for solar cells. Now, I don't have any real good source for that, but that's one of the things I heard in other YouTube videos, and seems reasonable to me, and I'm going to just use it. All right. Now, this is a simplified solar cell model, and we're going to talk about characteristics. R shunt, this resistor right here from positive to negative, this would be like the junction of a pipe here, is equivalent to leakage around the valve seat on a used check valve. R series can be equated to the flow resistance of the valve body and connecting pipes. The voltage across the diode causes a small current flow through the diode in a downward direction. Okay, this is an interesting way to model that. The current has to be large enough such that the voltage drop is created across the diode so that the V out and I out equal power out. ID has to be large enough to create VD, so V out is established. So if you don't have a voltage here, you don't get a voltage on the output of your solar cell or your solar panel. This diode performance is temperature sensitive, and IPH is the light energy that creates the current flow through the rest of the circuit. It's basically the water pump. And this is my little son, and it's going to feed the current here and out. good PowerPoint presentations you never read from the view graph. And since this is my first one for a YouTube video, I am going to read it. I photon is the light-induced current source. It only generates current flow. I in amps. No voltage potential is generated from the photon current source. This is where you're converting sunlight into energy. Now, a little trick I'll show is that the short circuit current through a solar cell is equal to the I photon times the current solar insolation divided by 1,000. 1,000 is where it's measured in the factory, 1,000 watts per meter squared. And if you know your current solar insolation, you can calculate what the short circuit current should be. In most cases, our shunt is large enough that the current through this resistor can be ignored. It does have some effect, but most of the time we can ignore it. Our series is small enough for most design considerations. There's not much of a voltage drop across it, and most of the time it can be ignored. There are a few calculations the small voltage drop has to be considered. ID and VD, the current and voltage through the diode, drives the whole solar cell performance. R series becomes a very important part when calculating these values. The open circuit voltage occurs when the I photon current, all the I photon current flows through the diode. No current flows to the series resistors. The open circuit voltage on it is about 0.6 of a volt per cell for a silicon solar cell. My particular solar panel that I own from Monday Nation is about 6.1 volts per cell, or 610 millivolts. The only time VOC is important is when selecting a charge controller for your solar system. Okay? Vmax power is important because that determines how much power you can put into your charge controller and how much energy you can put into your battery. All right? Most electronic devices have a limit as to how much voltage they can handle and how much power they can handle. In designing circuits, we usually put a derating on electronic components about 70%. For capacitors, we usually put a 50% derating on the capacitor. So if we want a 100 volt or a 50 volt capacitor, we use a 100 volt capacitor. When a solar cell is short-circuited, the voltage across the shunt and diode is so small, I'm going to say that the current is zero. Got that backwards. And it's zero going through both parts. Let's see if I can back up. I can't back up. I short circuit is equal to the photon energy, where it's proportional to the photon current. The error in making this approximation is too small to worry about. There are other error sources in solar applications, such how much sun energy do you actually get at a particular time of year, at a particular location, at a particular latitude. There's lots and lots of errors in determining solar insolation onto your solar panel. I'm currently working on another presentation for that, but before I got too carried away, I wanted to go ahead and make this simple analogy. The max power point of a solar cell panel occurs when the current through the diode is just large enough to achieve the max power voltage. This current through the diode on my solar panel is take the short circuit current and subtract the max power points current. For my Windy Nation, it's 5.9 minus 5.58, 0.36 amps, or 360 milliamps. And that's at STC, standard test conditions, which you get in the factory. Okay, next one. Now, this presentation of comparing a solar cell to a Plumber's relief valve is basically over. But I want to give due to Dr. Clarence Zener, give him his due respect. A Zener diode is specially designed, low power, or what an engineer would call a signal diode, designed to have a specific reverse breakdown voltage. I think in most of my designs I used a 6.1 or 6.3 volt Zener diode most of the time because it had the best temperature coefficient from a very high temperature to a very low temperature. A Zener diode requires the use of a current limiting resistor for the diode to work properly. Zener diodes are often used to create moderate quality voltage references sources in electronic circuit design. I actually use Zener diodes quite a bit in designing linear power voltage regulators. Power diode applications have no such current limiting features. Power applications don't want to waste the power. Reverse breakdown in power/solar diodes. Solar cells are a power diode. There's no two ways about that. The currents are fairly large, even though the voltages are fairly small. All right. Reverse breakdown is a component failure in a power diode or solar diode. The reverse breakdown voltage is an example of the Zener effect. Engineers want to emphasize breakdown in power applications as a bad thing by using the word breakdown as in broken, whereas Zener diodes are a good thing. And there's Dr. Clarence Zener. All right, this ends my first PowerPoint presentation. I'm going to try and publish it and upload it to my YouTube website and view it on my phone and my TV and see how it looks. Thanks for watching. All right, how do you stop?